There was a time when building an aircraft required an ocean of manpower. Thousands of people stood shoulder to shoulder inside enormous factories, hands gripping riveting hammers, teams assembling structural frames, engineers bent over paper blueprints. Everything moved forward through human strength, experience, instinct, and manual motions repeated for months, sometimes even years. But today, when you step inside a modern aircraft factory, the first thing that strikes you is not the number of workers. It is the organized silence of machines. Gone are the rows of people crowded around an aircraft fuselage, like in the last century. In their place are massive robotic arms rotating slowly under cold industrial light, automated gantries moving along wing body structures, CNC drilling heads working with near-zero tolerance, and laser systems sweeping across composite surfaces to detect curves and deviations too small for the naked eye to see. Simply put, in modern aircraft manufacturing, robots now perform most of the work that humans once had to endure with muscle, time, and mental stamina. A modern aircraft is no longer built by large groups of people, all working directly on the same physical body. It is born through an extremely precise, systematized chain in which robots, automation, and industrial software take the central role in shaping, drilling, cutting, joining, measuring, inspecting, and finishing. But to understand how large this transformation really is, you have to begin at the beginning. Today, the process of building a modern aircraft does not start with the sound of hammers. It starts with data. Before a sheet of metal is cut, before a composite layer is laid into a mold, the entire aircraft already exists as a digital model. Every surface, every joint, every curve, every allowed tolerance is defined inside a digital engineering environment. The modern factory does not merely build from drawings. It builds from a digital twin of the aircraft. That is critically important, because once everything has been digitized down to the finest level of detail, robots can take over most human labor. A robotic arm does not understand an aircraft the way an engineer does, but it understands coordinates, it understands start points and end points. It understands the angle at which a drill must enter. It understands how much pressure must be maintained. It understands which contour is correct and which one has drifted beyond the allowed limit. Humans once measured with rulers, aligned by eye, and checked by experience. Robots do the same through coordinate systems, sensors, algorithms, and the ability to repeat the same task perfectly thousands of times without fatigue. One of the most heavily automated stages is component machining. In the past, cutting and drilling large alloy panels for an aircraft body was physically demanding, time-consuming, and highly vulnerable to error. A slight deviation could affect the entire assembly downstream. In a modern factory, multi-axis CNC machining centers now handle nearly all of this process. Large blocks or sheets of material are placed onto machine beds, secured with exact clamping force, and machined by cutting heads moving along pre-programmed paths. Every curved wing body edge, every drilled hole, every joining surface is created with a speed and consistency that humans can hardly sustain over long periods. Robots are not only faster, they are more consistent. They do not suffer hand fatigue. They do not lose concentration in the 8th hour of a shift. They do not drift because of subjective feel. In an industry where every millimeter can trigger enormous downstream cost, that consistency is priceless. If you look at modern aircraft structures, especially advanced types that rely heavily on composites, the dependence on automation becomes even clearer. Composite materials are not like traditional metal. Their layers must be placed in the correct orientation, sequence, pressure, and temperature. A single mistake in one layer can alter the mechanical behavior of the entire section. That is why, in many modern production lines, humans are no longer the ones laying out material by hand, as they once did. Instead, robots handle the spreading, cutting, placement, alignment, compaction, and preparation of composite layers for curing in specialized heating systems. From a distance, it resembles a cold industrial ritual. A robotic arm moves slowly along a wing mold. A material placement head descends with absolute precision. Matte black layers settle onto the mold surface like skin being formed over the body of something enormous. There is no emotion, no improvisation, only precision repeated to the edge of perfection. And that is only the component creation phase. Once the process moves into assembly, the role of robots and automated systems becomes even more apparent. A modern aircraft body consists of countless major sections: frames, ribs, outer skins, load-bearing beams, belly modules, wing sections, nose structures, landing gear bays, and equipment compartments. In the past, bringing these large structures into position required large teams, heavy support rigs, and long manual alignment procedures. Today, much of that work is supported or replaced by automated positioning systems, large-scale assembly robots, intelligent fixtures, and laser measurement networks. A large structural module can now be brought into position by digitally controlled suspension systems. Reference points are read by sensors. The system knows exactly how many fractions of a millimeter the part is misaligned from its intended position. Then, a robot or automated correction mechanism moves it into the required coordinates. Humans are still present, but they increasingly do less brute force fitting. They supervise more than they lift, they confirm more than they shove. They verify system logic more than they physically wrestle with structure. Another process, once deeply associated with aerospace manufacturing, was drilling and fastening tens of thousands of connection points. It used to symbolize precise industrial hand labor. Today, in many advanced production lines, robots perform most of that work. Robotic gantries move along the aircraft body, self-positioning, drilling automatically, checking hole depth, and even carrying out part of the fastening operation. Where once a team of workers labored for days, there may now be a stable system capable of repeating the same operation with nearly unchanged quality from the beginning to the end of the shift. So what is left for humans? This is the most interesting point. Robots now do most of the work once done by people, but that does not mean people disappear. In reality, the modern aircraft factory is not a place without humans. It is a place where the human role has been completely transformed. Humans are no longer the primary labor source for work that is heavy, dirty, repetitive, or dangerous. Robots do those jobs better. But humans still decide how the system must be designed, which processes may run, what tolerances are acceptable, which data patterns are abnormal, when the line must stop, which module needs correction, and which section must be verified again by an expert. In other words, robots replace hands, but they do not fully replace engineering judgment. Especially in aerospace, where safety requirements are extraordinarily high, no one is willing to hand over all decision-making power to machines. A machine may perform with precision tens of thousands of times, but if its underlying logic is wrong, the consequences can spread across the entire production chain. So what is happening in modern aircraft factories is not the disappearance of humans, but the withdrawal of humans from physical labor into the realm of intellectual control. You will see fewer workers bent over around an aircraft body, but more systems engineers, more calibration specialists, more people reading sensor data, more digital quality control teams, more people working with digital models, algorithms, digital twins, and real-time deviation tracking systems. In truth, robots do not merely replace labor. They change the factory's entire philosophy. In the past, factories adapted to human work. Today, humans adapt to automated factories. Production spaces are designed around robotic movement. Platform heights are optimized for machine arms. Fixture surfaces are standardized so sensors can read them correctly. Parts are coded, tracked, and synchronized with digital data from before they enter the factory all the way until they become part of the completed aircraft. Each component is no longer just a piece of material. It is a data object with its own history. When it was created, which machine made it, which material batch it came from, how many inspections it passed through, whether it ever drifted out of tolerance or required rework, all of that can be traced. That is what makes modern aircraft manufacturing so different from the classic image of a factory. It is no longer simply a place where metal is assembled. It is a place where material, robots, sensors, software, and control logic merge to create one of the most complex industrial products humanity has ever built. But one truth remains: robots still do not do everything. In especially sensitive operations, in areas that require abnormality assessment, in checks where human experience still outperforms machine pattern recognition, people still matter. An experienced technician may notice a problem through an unusual vibration sound. An inspector may spot a warning sign that the system has not yet classified as a fault. A production engineer may decide to stop the entire line because of a small deviation trend that could become dangerous over time. That is why the near future will not be a humanless factory. It will be a factory where humans and robots coexist.